Okay, so a few words more about me. So I'm working in the IMIX-GAM group, standing for Gamma and X-ray Imaging in French, the French acronym. And actually, it's a pluridisciplinary team where I play the role of the mathematicians. I'm coming from applied mathematics and signal processing and image processing and blah blah, all data science today. And in the team there is also Christian Morel and Mathieu Dupont, who are coming from physics, particle physics, medical physics. We also collaborate with a lot of people from electronics and mechanics, and you will see why. So I will try to do a self-contained introductory course on X-ray imaging, trying to give an overview of the physics, of the technology, of the software development and the algorithms that are coming from. And I will basically make my course in two parts. A first part, I will try to do it in about 30 minutes, with a brief history and also a state of the art of the essentials in X-ray imaging. And the second part, more oriented with prospects. And prospects in X-ray today involves photon counting detectors, which are a new generation of X-ray detectors. And I will talk a lot about that at the end from a technological part and also from a software development part. So let's begin with the first part, and let's try to, let's begin with a brief history. I don't know exactly among you who is familiar with X-ray, or if you're working in other modality for your PhD. I don't know at all. Just raise the hand if you are working with X-ray, please. Okay, so let's go. So X-ray was discovered at the end of the 19th century by William Röntgen, who obtained the Nobel Prize of Physics a few years later for that. And the very famous pictures of the hands of his wife with the ring here has been published in the New York Times. So it's the very beginning of radiology, which will be pushed among all by Marie Curie in France. Okay, I think you all know Marie Curie, of course, for all her work on a lot of things about, among which radium and radioactivity. But one other thing that she made, what was important during the First World War, is the creation of this small car called Petite Curie. Actually, she borrowed some radiology equipment. She put it in the car, and she went to the front line where some people were wounded by weapons. And the idea was to help to make a good diagnosis on the spot, and to help to decide if the wounded people must be deferred and at the hospital, or can be treated and receive the surgery on the spot. So more than 1 million images were made at that time with the Petite Curie. And okay, so radiology basically involves 2D images. And when we are talking about X-ray imaging, most of the time now we are talking about 3D images provided by CT scan, computerized tomography scan. And we have to wait for the second part of the 20th century to see the CT scan, also called tomodensitometry, appear. And this has been mainly done by two people here, Alan MacLeod Cormack and Sir Godfrey Newbold-Hounsfield, who received jointly the Nobel Prize in Medicine in 1979. Their contribution actually was on two sides. First, more mathematical contribution, really, putting the physics through the Beer-Lambert law, which describes the absorption of materials, of X-ray by material here, and putting it with the radon theorem and radon theory, and discovering also that you can inverse the problem, and from radon measurements, integral measurements, you can retrieve here the F function, which is the unknown, and I will detail it later. Okay, and actually you can invert the problem, and you can theoretically solve from integral projection, retrieve F. And the other part of the work has been done by Sir Hounsfield doing the machine. And actually, he ended with a concept of a ring made of X-ray detectors, X-ray source that is turning around the patient, and at each position, making some radiography, 2D radiography. So several dozens or several hundreds of radiography are made turning around the patient. And at the end, this kind of machine has been done with this kind of images for a brain. Today, the CT scan, when you open it in the hospital, you see the CT scan are this very big machine with a bed in the middle where the patient is lying. Okay, the same shape as an MRI or the same shape as a PET scan. But if you are looking inside, actually here, you will see all the mechanics. You will see here the X-ray source. You will see here some X-ray detectors. This model is not with a full ring. And actually all this equipment, it will come back, I think. No. See? Yes, it's okay. All this equipment is mounted on a rotor, and everything is turning at a speed of several revolutions per second. So today, the limit of doing more images or reducing more the time of an exam is just a mechanical limit due to the forces that applies when everything is turning very fast around the patient, actually. Okay, so this was a really brief history overview of the X-ray discovering, development of radiology, development of CT scans, 3D. And now I will just give you a snapshot of how the raw data are produced and how can we deal with it. Okay, so let's try with a really toy example. I will not consider a 3D object, a 3D unknown object. I will consider a 2D unknown object, so this image. And I will just switch on one pixel here, okay? Let's assume that you have just some empty space and just an object here. And the idea is that you have an X-ray source placed at the infinity, so all the rays are parallel. Okay, it's either case. And actually, this object here will interact with the X-ray source, and you will get at the end, on the other side, the opposite side, a signal, a 1D signal, of course, which will integrate all the interaction that the X-ray are doing with the pixel. Here you can obtain this kind of signal. Okay. Then, what are you doing? The idea is that you will make the X-ray source turn around the object. You will start with the first position here, and you will obtain this kind of signal here in gray and in grayscale. And you will take this signal and you will put it here, continue to turn around, take a second signal which is different, and you will stack it with the first one. And you will have to make a full revolution around the patient. And of course, at each position for each signal, you stack everything with the previous one. And at the end, you obtain the raw data produced with a CT scan, with an X-ray machine, which have the same dimensions that the object. The object here is 2D, but it's 2D in space. And the raw data are 2D, but only one dimension in space. And the other dimension is the projection angle under which the projections are taken. Okay? So here you have the raw data are called sinogram. Sinogram just coming from the fact that if you are switching on one pixel, you will obtain a trajectory which looks like a sinus. Okay? And actually, this is the raw data that are produced by a CT scan. And of course, these raw data are completely not understandable regarding the object. You have to reconstruct them and to deal with them with dedicated algorithm. Okay, so this is a toy example in 2D. If you are focusing on the real life and you come back to a CT scan with a patient lying on the bed, with an X-ray source turning around him and with a ring of detectors, at the point, first thing, the X-ray source is not anymore at the infinity, and the rays are not anymore parallel. The rays are in fan beam or in cone beam, which makes some complication for the algorithm, but are tractable. And second part, each image that you are doing is not 1D anymore, it's an image 2D, so it's a radiography. And here you have example of 6 different radiography of the same patient taken at 6 different positions. Okay? But the principle is the same. So the idea is to stack all the radiography together and to make a full revolution around the patient. So when I've made a full revolution around the patient, the stack of data obtained, the raw data obtained is like that. So here my patient is 3D in space. My data are 3D. We are losing a dimension in space, so each image here is 2D in space, and the last dimension is still the projection angle under which we are taking the data. If you are looking this data cube in the right slice, you will see again the sinus shapes appear here if you are cutting in that side. So, okay, we are well dealing with typically data of CT scan. Okay, so now the point is that these are raw data, and how can we take this data and reconstruct back to obtain the 3D shape, the 3D anatomy of the patient. Okay, so basically, if you are putting the problem from a mathematical point of view, you are trying to invert not exactly the radon transform, but let's say the X-ray transform, which is slight difference. The radon transform and the X-ray transform are exactly the same when you are dealing with 2D images, but when you are going to 3D images, they are not anymore the same, because radon transform you will integrate according to a hyperplane, so the dimension -1, whereas the X-ray transform you will integrate along lines, so 1D trajectories. So from a set of 2D projection, when you are doing this kind of acquisition, you are losing one dimension, and it's not so easy to recover that dimension lost. So it's a complicated inverse problem in several ways. So let's try just to pose it. Let's take an unknown. Here I come back to 2D images. Here it's my unknown 2D image with a very simple shape in gray, which is my function of interest that I don't know. And I will integrate and make some acquisition according a theta angle. So I will just place again a X-ray source at the infinity, parallel rays, and I'm integrating, and I'm measuring a signal here. Actually, if I'm putting the framework, my function f of xy or st, depending on the reference that you are taking. Here, my projection according to the angle theta is one dimension here. It's just the integral of the function of the unknown function according several lines doing the same angle. Okay, and actually it's just an equation according one dimension. Just a few words about a thing. This kind of formulation is not only found in CT. This kind of formulation can be found also in TEP scan or in SPECT scan, so nuclear medicine, nuclear medical imaging. Okay, everywhere you have a tomographic problem. So here I can measure a collection of p theta, sorry, and I want to come back and estimate f from integral measurements of f. So first complication, according to the properties of the X-ray transform or radon transform, it appears that most of the time it is an ill-posed problem. I have some minutes to have some suspense, but it will come back. And it comes from the fact that if you don't have enough projection, you will not be able, of course, to reconstruct in 3D. One example, very simple. Here you have two different objects that are giving exactly the same set of two projection. Here you have just 4 pixels, let's say at an amplitude 10, and here you have just 2 pixels at an amplitude 20, twice 10. Of course, the projection will have the same amplitude, and you will not be able from this set of two projection to say if the object initially that gave this projection is this one, or of course, if you understood, there are many other possibilities. Okay, so you need more projection. You need to look at the object from more angles. And of course, theoretically speaking, I will come back it later, but I will not put the equations. Actually, it's not a teasing, but you will theoretically need an infinite number of projection and an infinite number of angles to be sure that the reconstruction will be unique, but in the fact, you will never have an infinite number of projection. So the second part is the fact that this inverse problem is ill-conditioned. What does that mean? It means that the radon transform is not at all very sympathetic concerning the noise managing. Actually, it amplifies the noise. The spectrum of the matrix representing the radon transform is really Hill conditions. So there is a lot of, let's say that the eigenvalues of the spectrum, the lower eigenvalues are falling asymptotically to 0, which is really bad news for that. So some slightly different projection set, depending on the noise, can occur to significantly different solution when you are reconstructing it. So you have to deal with noise, actually. Noise is an important question in that problem. And practically, as I said just a few minutes ago, yes, sure.
Why do you say that such bad
because because the condition number of the Radon transform is really high, actually. And actually, if you don't cut actually the spectrum of the system, of the matrix system, of the matrix of the Radon transform, with a kind of SVD or whatever you want, the noise can explode, actually. But cutting, okay, a shortcut would be to say if you are cutting, because the spectrum is really continuously going down. If you are cutting too much, you will correctly manage the noise, but you will lose high frequency also. So high frequency in images is really important because it's the contours, the shapes, some details that in medical imaging you don't want to miss. I mean, some small lesions or something like that. So it's a complicated trade-off, actually. So you have to manage it by all the way you want, but it's a complicated. It's a
so just to understand better, what would be a better fall-off of the eye lens?
well,
What's the thing you like?
I would like not going to zero, of course, or I would like to sharply decrease to zero. Okay, it would be a better configuration. Okay. Actually, in other modalities, you have some more. When you are describing the physics, there are more favorable case than the Radon transform. So practically, each solution of any algorithm dealing with raw data will be an approximation of the solution, actually, because you don't have an infinite number of projection. You don't have to put a model of the noise. And you know, when you are solving an inverse problem by dealing with the noise and adding some a priori information in the inverse problem, you are already starting to design yourself your solution, and you are trying to, or well, let's say to not to take into account only the data, actually. I will come back. So it's complicated. Why are we doing that? Of course, if you have the 3D shape, you will have a greater freedom of data display. Here you have a volumetric appearance of a foot with the superposition of two different kind of tissues. But the main thing is that you will get some better contrast if you are reconstructing in 3D. Let's just to understand that, you will take 2G objects, which is your unknown function, and here assume you have, let's say, a tumor here with an amplitude of 10, surrounded by soft tissues with an amplitude of 1, for instance. And of course, the contrast in 3D in the original object will be of 10. If you are just projecting and integrating, you will just lose some contrast. Here, the contrast on the projection of the radiology will be only of 13 over 4. So let's say at least 3 times lower. So you have an interest to reconstruct and to make the effort, at least to gain a contrast. And the biomedical imaging is basically a contrast imaging. The information for the diagnosis is based on the contrast. So you will try to get the better contrast that you can. So, coming back to everything, putting everything together. The standard CT basically measures the semi-transparency of the material to the X-ray. So you have X-ray source that sends X-ray on object, and the material will absorb some X-rays, or let some X-ray going through, and then you have on the opposite side the X-ray detector. You are taking some radiography by turning around the object, so several radiography, making a full revolution with, let's say, as most image as possible, let's say just that, and at the end you will put this data and you will put it in the reconstruction algorithm to come back to the object. The object is 3D. You have to look at this reconstruction. Most of the time in medical imaging, the thing, I think, okay, everything is familiar with that, I think. The way to display some 3D image is to look at slices. So the 3 main slices usually interpreted are the coronal, sagittal, and transverse slices. So transverse slices are separating up and bottom, sagittal left and right, and coronal behind and in front of. Okay. So one comment about the number here or projection that are required to make a good reconstruction. Okay, infinite number of projection is not possible. Okay, we are living in a numerical world, and actually all the images are pixelized and all the reconstructions are voxelized. So you have a resolution in terms in the image, in the raw data, you have a resolution in your reconstructed volume. And of course, from that point, you can try to start writing the Shannon theorem of sampling and try to adapt it to the context of 3D tomography. And if you are writing it, it's not so easy, but if you are writing it, it will give you an idea of the number of projections that you can hope that you must acquire to be able to perfectly reconstruct your object if you are under the Shannon assumption saying that your image is band limited, which is not the case in the real life, but which gives you some kind of guarantee and some kind of framework to do the job. So actually, the number of projections that you have to take around your revolution, it depends, of course, on the size of the pixels, and depends also of the dimension of the geometry of the images. So you can express some things. Typically, for this kind of image, so I'm showing you some image that have been taken at the laboratory in a microcity for small animal. We are taking about one image every half degree, so 720 images for revolution, and it's enough to produce some nice reconstruction here. Okay, so when I'm saying that, there are some hidden layers that are not tricky at all, and I will not detail that in that course. But there are some concerns about photometric calibration. What is that? Actually, if you are taking X-ray detector, if you take 2 pixels that are neighbors, your 2 pixels have to give you the same measurements if they are illuminated with the same source. So they must be, the electronic must be homogeneous, and the sensor must be homogeneous, etc. And of course, this is quite well under control, but not so easy. The point is that if your pixels are counting a difference of, let's say, 1% of the measurements, when you are going through the reconstruction process, you will obtain some artifacts that can be visible, even if they are counting 1% difference, because the radon transform, once again, is very sensitive to that and will produce artifacts very easily. So there are some challenges about photometric calibration. Another one is geometric calibration. What is that? Actually, the geometric calibration comes from the fact that when you are inverting the problem, you need the raw data, of course, but you need also to describe all the distances, for instance, between the X-ray source and the X-ray detector, between the object and the X-ray detector, the relative position of everything. And typically, the spatial resolution that you can expect in the 3D reconstruction will be several hundreds of micrometers, let's say that. So you have to be precise in the geometric calibration at least half of, less than 100 micrometers. So you make your measurements very precisely, and of course at that time you have to have a calibration process that allows you to know the distance at that precision. Of course, you have software developments. Okay, you have the challenge of designing the algorithm. I will talk about that, but you also have the challenge of making them fast enough to be usable in the clinical context, where a doctor must not wait for 1 day to have the answer, and it's a challenge actually. Okay, so now I will say a few words about the 2 main classes of reconstruction algorithm that are, let's say, the state of the art. It's classes of algorithms, or many algorithms, and today again we have some PhD theses that are looking and trying, looking at some new algorithm and trying to make some algorithm evolving. The 2 main classes are the following. You have first the analytical method, they are called analytic in the community, and the iterative methods. Okay, analytic methods are coming from the 80s, based on the Fourier slice theorem. Let's say what Cormac wrote at the beginning. And the iterative methods are the most used today. There are a lot of algorithms. I will present one of them. So first, analytic methods. They are based on the filter back projection. Okay, you can write 2 pages of equation, invert the Fourier transform, the radon transform, and blah blah blah. But at the end, what's coming is that you are taking your projection Here, there are 3 views in 1D for a 2D object once again. And the principle is to make a back projection, saying, okay, I will take the first view. My signal is there. Okay, so I have some positive signal here. In my reconstructing image, I will take this signal and back propagate it on all the pixels that correspond to the direction of acquisition of this signal. And then I will take the second one and do the same thing and make the sum with the previous one. And then the third one. And if you have, okay, it's an example here with 3 views. If you have many views with a revolution around, at the end, making the sum of all these back-propagated signal will give you some kind of signal here, some kind of object here, circular, which is the object that provided this signal, okay? At least not exactly. This object is not exactly the one that produced the signal. Actually, the real objects have sharp edges and accurate edges. And actually, if you are writing the equation, what is needed, what is required, is to pre-filter your signal before back-propagating. Okay, so this is just the Fourier slice theorem saying that you have to take your signal, each of your signal, go to a high-pass filtering, high-frequency filtering, with a filter which is the ramp filter, so it's a linear filter, linear Gabriel in the Fourier space. Okay, and if you are pre-filtering here, the signal are there, the shape clearly of the edges are accurate. And if you are back-propagating it, you will get back with your correct object. So the filter back projection in 2 slides and with 2 images is based on this principle, of course. There are many questions behind. But it's enough to be, it has been a very, very used thing and algorithm. And it has been defined for parallel rays. It has been also defined for fan beam rays, for X-ray source with fan beam. And it has been even defined also for cone beam CT. So cone beam CT is quite complicated problem because you are losing some theoretical guarantee of reconstruction, of exact reconstruction. But it has been adapted in a way such that it has been used for years for the reference algorithm. Why is it so used? It is very fast. Actually, you just have a pre-filtering and then back propagation. Okay, let's say that in a clinical context, in less than 1 minute, and I would say now with the computers in less than 10 seconds, you have the solution, so it's quite cool, okay? But there are some drawbacks. First, the exact reconstruction, I said, is only guaranteed for an infinite number of projections that you don't have. If you don't have an infinite number of projections, some artifacts may appear. Okay, everything is pixelized, you are respecting the, let's say, the Shannon criteria. Some artifacts can even appear because in the Shannon criteria you are assuming that your image is band limited, but it's not the case. Okay. The ramp filtering that you apply first in your projections is a high pass filtering. So it will amplify the high frequencies, and in the high frequencies you have the edges of the image and you also have the noise. So it will amplify the noise. So you have to accept that in the images some artifacts are coming, some noise is coming with sharp edges. And there is no way in these equations to deal with the noise. There is no noise modeling to overcome that. And there are some also ray artifacts due to incomplete data and diffusion. Okay, so just one visual example, a quick one. Once again, here you have the original, the ground truth object, simulated one, of course. Here you have some filter back projection that are coming with very good reconstruction. If you forget to filter, of course, everything is fuzzy, everything is smooth. And of course, the ray artifacts are coming from the fact that you don't have enough ray here, a number of projection. Or sometimes, for an angle, you have some dead pixel, some measurement, or saturated pixel, some measurements that are not coming correctly. And you have to deal with that. With that model, you can't. So let's try to illustrate that with real data. I don't know if there is some possibility just to switch off just this one. I don't know. Or just a few minutes to switch off. Not this one. No. Don't sleep. Non, c'est juste celui-là. Ah, c'est peut-être ici. Peut-être ici. Non, ça c'est le tableau. Okay, let's do it. Okay. What I want to show you here, 4 images. 3D mouse that has been scanned under anesthesia, of course, with everything correct from an ethical point of view with biologists. It has been scanned. Here you can see the slice corresponding to the lower part of thoraco-abdominal part, thoracic scan. Here you can see vertebra. Here is just just their hands. And here you have almost no contrast because you are in the abdomen. Okay. First part is that, I don't know if you see it, you have some kind of circular shapes, very tiny, but circular shape, concentric circles, which are coming from a non-perfect photometric calibration. 2 pixels are not counting exactly the same thing. With less than 1% difference, it results in some circular shapes that are acceptable here. Okay. Now let's do a first exercise. I will reduce the number of angles by a factor 10, which is clearly a lot, just to see the artifacts. And here with the high dose, because here there's almost no noise, quality of image is really good. Just if you are reducing the number of angles, you can see some X-ray, some strict artifacts, right lines that can appear. I don't know if you see it. I'm sorry. Yes. Okay. And here another thing is that from there to there, from left to right, I'm reducing the dose by a factor 25, meaning that I will just lower the intensity of the X-ray source and send less photons by a really big factor because it's research, okay? And to see how the signal-to-noise ratio of the data impacts the reconstruction. And you can see that with a full number of projection and no streak artifacts, you can here see that the image is a little bit more grainy. I think the word is the same in French and English. Here you have some kind of high-frequency fluctuation that you almost no see anymore the circular artifacts. And if you are combining two problems, here you can take the image and go to garbage. Nothing is exploitable there. So this is the 2 principal source of noise that you can obtain with the 3D reconstruction, with the filter back projection, or any other Fourier-based method based on this principle. So what can we do better is to go towards a second class of algorithm, the iterative reconstruction methods. Okay. So the iterative reconstruction method is based on just one thing, saying that at the very beginning, everything is numerical, everything is pixelized, everything is discretized. No more integral equations that I didn't show, no more Fourier transform, and blah, blah. So here you assume that your object is discretized. So if your real shape is there, then you will lose at a very thin resolution, you will lose the shape of the oval. You will have 2 acquisitions that will be square, but okay, let's do that. And what are we doing? We will try to recover the f function, meaning we will try to recover a vector of f. Here is just an extract, a zoom on 4 pixels with 4 unknown, f1, f2, f3, f4. And actually, we will model the acquisition, saying that if I have an X-ray here coming from the bottom and going here to give me the pixel value P1 in a detector placed here, P1 will be clearly a linear combination of F1 and F3 with some coefficients. And I express here the same thing, P1 equal to a linear combination of F1 with the coefficient A11 and F3 with the coefficient A13. Of course, no contribution for P1 from F2 and F4, according to the drawing, is obvious, but for a more general model, you will add every unknown value of the vector, which some coefficient there that will be equal to 0 in this example, of course. And for each pixel of the detector, and for each position angle of the detector, you will describe and you will write the model of linking the acquisition P1, P2, P3, P4, so the projection vector, to the unknown that are here, and you have a linear system that appears with a very simple product of matrix vector, linking the unknown f vector that you are looking for to the measurement, the observations, the pixelized projection P, with a matrix made of coefficients describing the geometry and many other things inside. So typically, the basis of the iterative framework is on this model, actually. And after, you will deal with that. So this matrix A is called in the system matrix, describing the system. What can be found inside? First thing, it will describe the geometry. So how can we describe the geometry? How can we choose your coefficients? First, very simple way, one or zero. This is the Dirac model. So roughly speaking, if your pencil beam is going through this pixel, you will put 1. Otherwise, you will put 0. Very simple model. If you are using it, the images will be not very good quality. Let's go to a more specific model, linear model or integration length, saying, okay, this pixel of measurements will be a contribution of all the voxels inside this pencil beam. But this voxel will probably provide a bigger contribution than this one because the length of intersection between the line and the voxel is smaller. So I will choose my coefficients proportionally to the length of interaction. And this model actually is a good trade-off because the quality of images is really good. It describes quite well the geometry. And we are just talking about line of integration, so you can write some geometric rules. And the computation is not so complicated. It's not a big complexity. So that in the reconstruction framework, it can be computed online, on the fly, and it's quite cool. But you have the gold standard, which is the volumetric model, not taking into account the fact that you have a line of integration, but you have really a pencil with here a width, and you will compute not anymore integration length, you will compute some area of intersection. Of course, the complexity is really bigger. The images are really of better quality, but you will pay it with a computation time which is significantly larger. Okay. But of course, in the system matrix, you can also introduce all the artifacts. Okay, assume that your detector has a dead pixel, for instance. Well, you say that, okay, this measurements is not valuable. I don't want to take it into account. In the system matrix, I will put some 0 on the line, on the corresponding lines, and then the reconstruction will take into account that you don't have to take into account this pixel. Okay, so you would not propagate some wrong information. You also can introduce some physics. I will not talk about that, but actually, when you are producing some X-ray images, the physics that produces some X-ray imaging is mainly the photoelectric effect, saying that the X-ray photon can be absorbed by the matter or going through in the right line, rectilinear trajectory in the matter. This makes the contrast. But of course, you have a lot of other effects, among which diffusion, Compton and Rayleigh diffusion, mostly Compton diffusion, saying that the photon will just deviate from its original trajectory and arrive on a pixel that is not in straight line with respect to the source. But in the mathematical model, you don't model that at all. So this produces some noise in the data. And a way to do that most of the time is to develop some hardware with some collimators to select only the photons that are coming in a rectilinear trajectory. There are some problem of dose reduction and blah, blah. But from a software point of view, a way to deal with that is to put in the system matrix some additional coefficient that take into account the diffusion model and trying to compensate this diffusion model into the reconstruction. Yes?
Very basic question, but so since the one problem is the cylindrical geometry, why have this kind of pixel or voxel grid? Why not having like cylindrical symmetric?
It's not cylindrical actually because actually the source. Okay, there are two main geometries. The first possibility is to have a fan beam geometry. So the patient is on the bed. You have the X-ray source, which is going sending some X-ray with a fan shape but in the depth dimension is very reduced. So then the trajectory of the bed will be like that, and you will have an equivalent of helical acquisition, and you will deal with that position by position as if you were, well, let's say just a fan beam 2D, and it's quite easy. The other possibility is not so cool. You have X-ray with the cone beam, and at that point, well, what was the question exactly at the end?
Why have like a Cartesian grid?
Yes. 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 With the cone beam, actually, the cylindrical coordinates will not be adapted really, actually. But the coordinates are really a real problem when you are dealing with, when you are implementing the algos. I'm not sure they are good. Yeah, polar coordinates are definitely used at the point, but neither spherical, neither cylindrical coordinates, actually. It does not make the problem easier, actually. Okay, so I'm done with that and the diffusion in IG. So another point is the dimension of the problem. Actually, this kind of linear problem, you are able to compute the solution with the pseudo-inverse matrix of A, which is this kind of formula, if you are able to compute these matrix computations. You will have a kind of equivalent of least square solution with the pseudo-inverse problem, but the problem is the size of the problem, actually. So if you are just writing the size of A and the number of lines and the number of columns depending on the number of projections, and the size, the spatial dimension of your images and your 3D volume that you want to reconstruct, you will at least come from 500 million equation and 500 million unknowns, which means 500 million lines and 500 million columns. It's the lower bound, actually. So actually, when, even if you understood that this matrix, most of times are sparse, a lot of coefficients are equal to 0. Let's say that 1 to 3% of the coefficients are usually not 0, but even with the reduction factor, which is favorable, the dimension of the problem make that the matrix system is not even storable on a hard disk. So forget the RAM, and forget the on-the-fly, and forget the pseudo-inverse. So this is the only solution. This is the only reason that, which makes that we have to design some iterative algorithm to approach this solution iteratively without any storage of the A matrix, actually. So we want to minimize this cost function. Typically, it's an example where I put the least square because it comes from a Bayesian optimization, assuming that the noise is Gaussian. At the end, I want to find my unknown in a space of n, a vector of a dimension n, such that when I go through, I take my unknown and I go through the system matrix, I obtain a projection that are similar to the one I measured. So it's the classical data fidelity term for solving an inverse linear problem. And I will construct some iterative algorithm. So the generic thing, who is familiar with the iterative algorithm in your field? Okay. For the PhD students? Okay. Half. Okay, let's go. The canonical scheme of iterative algorithm is the following. You will start with an initial guess of your solution. Maybe you don't know anything, you put 0 everywhere. Okay, so it's my F0, and at each iteration you are doing the same thing, saying, okay, I am at the iteration n. My current estimate is F, here, F over n. I will project it. I will go through the matrix system that model my system. I will obtain the measurement, the observation, that I would have obtained with my system if my object is Fn. And I will then compare my projection to the real one that I measured. From that, from this comparison, you will design a similarity factor, distance, something that reflects the fact that maybe these two quantities are the same or very close, or maybe they are very different. And from that indicator of similarity, you will deduce and choose a correction factor that you will apply to your current estimate Fn. This factor can be in addition, in multiplication, depending on the choice of your factor, depending on the choice of your similarity index, you will have a large possibility of algorithm, of course, with some insights. And from that, you will estimate the current estimate at the iteration n+1. And then you will loop until convergence. So until convergence is a big word. actually, first thing is that you have to design every choice here in the here and here at least, so that you are sure that if you let your algorithm converge a million iteration, a billion iteration, you will converge. Meaning that at the end, first you will minimize the cost function that you want to minimize, and you will also be sure that it will stabilize at the end. Okay? So these are theoretical guarantees that you have to write and you have to check and you have to ensure that everything is well. But the point is that I don't want to wait for the billion iterations because it's really a lot of time. So how many iterations should I use so that it works? Okay, it will depend on the properties of convergence of the algorithm, the speed of convergence of the algorithm, which is one of the parameters that are important. Okay, that can be sometimes theoretically studied before, but most of time mostly practically studied with a lot of example as saying, okay, for this kind of images and for this algorithm, I have to wait 100 iterations and to be okay. So it's typically a very important question, but a property that you can study. Just a few examples to illustrate, very toy example. Okay, I will take an unknown object here, just 4 pixels, 2 by 2, 1, 2, 3, 4. Okay, so if I'm just producing 2 sets of projection here, I will obtain the blue projection from bottom to up for the X-ray source, and the red projection here for left to right for the another position of the X-ray source. I will obtain 6, 4, and 70 and 7, 3. Okay, now let's go. I'm trying to estimate my F. I'll start with an initial guess of 0 everywhere. How does that work? I will go through my system matrix A, so I will generate my first projection, here 0, 0. I will compare it to my measurements here, and I will choose here to make the subtraction between the two projections. So at the end, the subtraction is still 6, 4, of course, and I will backpropagate. This is my correction factor. I will say the 6 is coming from that direction. I will put 3 and 3, the mean, or the half, sorry, and the same thing for 2. So at the end of the first iteration, I have that 3, 2, 3, 2. I will generate the second projection going once again through the matrix system, obtain 5 and 5, and compare to my measurements 7 and 3, subtraction 2 minus 2. I will backpropagate. So plus 1 here, minus 1 on the second line, and at the end it's magical. 4 equations, 4 unknowns, very well chosen toy example. It works in 2 iterations, okay? So at the end you come back to your solution in 2 iterations. So basically all the algorithms are working on this principle, of course with very sophisticated things. Okay. A last word on this first part about the computation time and the complexity, which is an important thing, actually. Well, when I started to work on that field, it was in 2009, lots of years now. Okay, the development of hardware like GPU and blah blah was not at the point where it is now. And usually, all the iterative algorithm were clearly the trend, but there were some real questions about the computation time. From a clinical context, you don't need to wait 1 hour or 2 hours to have the images. You can do it for one patient, but you know that for X-ray and CT scan, several patients are coming in 1 hour. So if you are multiplying by the number of reconstruction that you have to do, at the end of the day, at least the doctor have to make the report. So he must have the images at the end of the day. And for reconstructing one image, one volume, one patient, it could take 2 hours. So impossible. So actually, the iterative algorithm were the trend, were in development. But clearly, most of time, the idea was to think a lot about warm start here, warm initialization, finding the better initialization possible, trying almost to solve the problem before, to do such that to make the fact that you need a very few number of iterations to converge. Actually, the idea was to use the filter back projection first, noisy results. It will be the initialization, good idea. So that after that, the iterative algorithm will just clean the noise and it will be okay. Okay, so today we have some computation capabilities that are really important. And to accelerate the process of obtaining the image, there are two possibilities. You have, of course, the hardware way, so use some very powerful computation things. But you also have the theoretical way, trying to conceive some algorithm that requires less iteration, that are smarter, and blah, blah. So I will talk about one example, which relies on the order subset idea, saying a magical thing, saying, okay, take here all the projection that you have. Here I have only 8. It's a toy example once again. And actually, I will reconstruct not the 8 projection altogether. I will split my set of projection into 2 sets of projection, 2 sets of 4 projection, or 4 sets of 2 projection. And I will reconstruct, I will apply the same algorithm in these 2 sets or 4 sets projection. How does that work? Actually, let's take the idea of the example of 2 sets of 4 projection. At each iteration, I will have 2 steps. My first step will be to estimate f1 prime, an intermediate estimation, from the initial guess, only from the projection of the subset S1. Take the intermediate estimation, and then estimate f1 at the end of the first iteration from the intermediate solution, and using this time only the subset S2. Okay. And actually, you can prove that if you are just doing the reconstruction like that with the same number of operation, so it's the same computation time, it's the same number of addition and multiplication, just in a different order, actually you will converge, you will obtain an acceleration factor of S, which is the number of subset. This magical trick comes with an approximation in the inverse problem on the structure of the A matrix. But this approximation actually is quite robust and quite acceptable. So an illustration of that is that if you are, I will apply the maximum likelihood expectation maximization algorithm, which is an iterative, one of the iterative algorithms that are existing. And I will show you the evolution of a reconstruction for 40 iterations here of an object. Okay, let's try to be honest. This example is not CT, it's PET imaging, but it's tomography, the same thing, okay? It's emission. And you will see that you will have the correct reconstruction at the iteration 40. If I'm using the order subset approach with 4 subsets, at the 10th iteration, I have the same solution, and with 8 subsets at the 5th iteration, I have the same solution. The only constraint that I didn't mention is that in each subset, you will need to have enough projection. So, of course, my toy example of their 2 projection in each subset is not feasible. You have to at least to have, I don't remember exactly, but it's between 5 and 10 projection per subset, but it works quite well. It just requires less iteration, and it works very well. I may have a question. No, it's okay. Okay, so I'm over with the first part with algorithm. Yes, if you have a question, some question about that, yes.
Thanks so much. It's very nice.
Thank you.
Maybe 2 questions on the,
Sure.
on the recon.
Yes.
I think at some point you mentioned the model-based reconstruction. So that's something we have in the MRI field.
Yes, sure.
Where we construct the reconstruction with, for example, the T1 relaxation,
Yeah.
the T2 like physical
Mm-hmm.
information. How does it work here in this case?
It works exactly in the same way. I mean, the algorithm, okay, I will talk about that at the very end, but we can discuss about that now. The mechanical of the inverse problem does not belong to the CT field or the MRI field. It does belong to the optimization field or inverse problem field. So actually, all the models are the same. Basically, you still have some data fidelity term, plus most of the time some regularization term, which will include some a priori information, a high-level knowledge about your physics, your context, your problem, and most of the time the behavior of the solvers are really problem dependent most of time. So MRI, you have some, you are lucky because your operator is a Fourier transform, more or less, and Fourier transform is a really nice operator because it is invertible, well conditioned. You can mix it with a lot of decomposition basis for the regularization. It's quite cool. But basically, okay, let's say the main class of algorithm are based on gradient descent. I don't know which algorithm are you using, do you know? Dependent implication. So most of the time you have gradient descent. That can be accelerated or not. There are two, I will talk it later, but you have some direction of acceleration which belongs to the Nesterov classes, the momentum techniques. And you also have the possibility of using some Newton-like application, using some second order information into the inverse problem to accelerate it. It needs to, most of time, to use additional matrices that you have to invert computationally speaking. It's not so easy, but you have some subclasses of Newton-like problems with low memory usage to be efficient. I think that one important thing in this class is the fact that when you are using some regularization, some a priori knowledge, you are traducing it into an additional cost function that you want to minimize. So you are trying to say, okay, I don't know, for the T1 relaxation, it's, I don't know, the constraint, typical constraint is what? Typically for the T1 relaxation, which typical constraint are you using?
Like you could put everything in your, like you could do the, for example, for T1 mapping, you know the recovery, the exponential recovery, so you could put that as a model in your iterative
Okay.
as a constraint, for example.
As a constraint, okay. So
we know the exponential model, but
okay.
I'm wondering if you have this kind of
So I think that typically this kind of constraint is well documented, and typically it's the inverse problem with constraints that can be nonlinear. Okay, everything is okay if it is differentiable and if you can derive your constraint. Then after that you can go into the gradient descent scheme, and everything is okay, and you come back to the class of algorithm that you can manage. So we can discuss it later if you want, but
we have time this
yes, sure.
I'm very glad that you're going to start talking on the PCCT scanners.
Yes.
The new scanners, I'm very happy, but I know that the data is huge. Like
Yes.
Multiple gigabytes, maybe hundreds of gigabytes. I know it's huge.
Yes.
If you put on top of that very slow iterative reconstructions, like you mentioned, like
Yes.
how long does it take to reconstruct PCCT data with such iterative reconstruction?
This is a very good question. If you are okay, I will answer to this question a little bit later, because I think my answer will be well understandable. Okay, but I will come back to this question if I forget. Tell me. But you will see that in some case the volume of the data are the same. In some other cases, you're completely right. It's a really complicated problem. And in this other case, everything is not at all used in clinical context yet, and everything is working, and it's still an open question actually. So now I will, yes, sure.
Just last question, I have a very stupid question, but since you are acquiring in a circle,
Mm-hmm.
is it really worth it to acquire the two halves of the circle, or is it the same if you acquire left to right or right to left?
If you have some parallel rays, half of circle will be enough. But in the real life, parallel rays are just existing maybe in synchrotron, where the source is really, really far, and yes, approximation is a good idea. In the real life, it's still fan beam. Okay, in the clinical context, clearly, it's not parallel at all, and you need a full circle to have some completeness of the data. Okay, part 2, prospects and use of the X-ray detectors. So we will talk about photon counting detectors, which is the technological breakthrough into X-ray detectors that occur, let's say, in the last 15 years. I will try to be more precise. So the main motivation at the very beginning was to say, okay, we will go from black and white to color CT, spectral CT, which is called spectral CT. Color will be spectral, actually. And the analogy, of course, was with the TV. I don't know how many, but 50 or 60 years ago. I was not there. So, what are we doing? The this story comes from the high energy physics and the CERN experiment, the LHC, which discovered the Higgs boson with a Nobel Prize in 2014, I think, or 15, I don't remember exactly. And one of the experiments at the LHC was the ATLAS that you have here, which is a very big calorimeter, which try to detect some high energy particles that occur very fast. 4 million collisions per second. You have to detect fast. You have to be sure that you identify the good particle with the good trajectory. You have to be very precise. There is only one particle, so you have to detect one particle and not a bunch of particles. So a lot of challenges for which the electronics and mechanics answered positively. And one thing that was a product of that was the hybrid pixel technology. Basically, we are calling it hybrid pixel because you have a classical sensor, typically silicon, for instance, and the charged particle will make, let's say, a photoelectric effect, produce charge inside in the semiconductor, and through, for instance, here through a bump bonding, so a small ball made of metals, it will conduct the charges. Charges here to an electronic dedicated to one pixel, so each pixel have its own electronic. And we are not anymore in the context of charge coupled detector, CCD, or charge integration detectors, where the electronic usually is at the end of the line and is reading all the pixels of the line. So each pixel have its electronic, so it can run very fast detection. And the other thing is the photon counting mode. And the photon counting mode here comes from the fact that here the electronic here will use a counting ASIC, which is an analog part with a pre-amplifier of charge because they are very small signals. And after that, I will just put a counter, +1 or 0. If the particle has made a photoelectric, I will make +1, otherwise 0. So at the end, the nature of the measurement is not the same than before. Before, during the acquisition time, you will collect all the particle here or here, the electronic charges produced by all the particles that came from the acquisition time, and at the end, we put everything together, and we are measuring a number of charges, integration charge. Now, during the acquisition time, we have an electronic which is working very fast. A first photon is coming, photoelectric effect, produces some electronic charges coming through the electronic. Okay, I have enough charges. Yes, I had one photon, +1. Still in the acquisition time, a second photon is coming, charges +1. We have 2. And maybe at the end of the acquisition time, the measure is 10, because during this acquisition time, 10 photons came and produces some photoelectric effect. So during the acquisition time, we were able to separate and to analyze individually each particle with, of course, a dead time. Let's say less than 1 millisecond is not possible. 1 millisecond is possible. So 1 millisecond saying that you can expect to make 1,000 images per second if you want to reduce at the lower. Okay. So the fast acquisition property provides you, if you are introducing it into application, to slow motion video, because you have some X-ray architecture that allows you to make several hundreds of images per second. So even if we are filming Usain Bolt, we will see the course of Usain Bolt in X-ray. Now we are able to do that. It was existing, of course, in the visible domain, not in X-ray domain. Okay, but the main part, actually, the most important part, is that this counting ASIC is equipped with some thresholds, some energy thresholds. So, what does that mean? Here you have an example of an acquisition curve. In X-ray, in the x-axis, sorry, you will have the time in nanoseconds, and here in the y-axis, you will have some in red thresholds that are defining some bins of amplitude. Okay, and the idea is that, okay, here, if I have a signal at that moment that is above this bin, I will count one particle. if I have a signal here above the bin, well, lying in the number 2, I will count one particle also, but in the bin 2. Same thing here. This I will put +1 in the bin 4. So my measurements is more than the number of photons. My measurements is a kind of small spectrum of number of photons. So at the end, on this example, I will have 1, 2, 3, 4 photons in the bin 1s. And I will have 1, 2, 3 photons in the bin 2, 1 photon in the bin 3, 2 photons in the bin 4. This will be my measurements. So number of photons and selection in energy, because what I didn't say exactly is that here the y-axis, here it's the scale is an electron volt of voltage. It is equivalent to the energy that carries the photons that is coming. Yes.
In this photon counting strategy, like is it the typical photon budget that is available in the experiments, or do you have to artificially reduce the number of photons or like reduce the time over which you integrate?
Okay. This is during a lot of years the problem of this kind of architecture is that above 1 million per photon per second per pixel, you will saturate everything. Or the clinical context requires 2 orders of magnitude above. Today, I think the things are quite under control, and they are able to support 10 to the 8 photon per second per pixel with some strategies that are under control. But yes, it was a big thorny part at that point.
But
okay. Yes.
along the same line, to me it has always remained mystery in photon counting. Take for example the second bump there.
Yes.
So how you said that we count 1 photon in bin number 2.
Yes.
But couldn't it be just by chance that you have 2 photons that arrive nearly instantaneously?
Yes.
And
Okay, this is called the pile-up effect, and this is a problem. Okay, the near instantaneously means at least mean actually in less than 1 millisecond. For the ASIC on which we worked, it was the limit. Under 1 millisecond, you will not be able to differentiate 2 particles. It will be the time resolution actually, and of course, on that point, I can do anything. Okay. Yes.
Just to be sure, so all the photons in the beginning, they are exactly the same or in a spectral range that is very limited. So this dispersion of energy is due to interaction with the sample, or it's right from
No. In the clinical context, if you are going to a synchrotron, you will be able to obtain a monochromatic bin. Okay, 1 energy and go. But in the real life, if you are going out of the synchrotron, no beam is monochromatic anymore. So you only have polychromatic beams of several energies. You know the spectrum more or less, but when you switch on, everything is coming. So, okay. So one important point on that is the capacity to be selective in energy. And the first thing is that just with one threshold, you will place your measurements above the level of the electronic noise, which means that with detector, you don't have any more dark noise, which is the classical in-charge integration detector. So in particular, with very low level of radiation and a level of signal, you will be able to suppress the dark noise and to keep a signal-to-noise ratio which is really interesting and better than with CCD. If you are introducing it in terms of safety of health, actually, it means that you will hope that if you are reducing the intensity of your X-ray source, so the integrated dose for the patient will be lower, then you will hope to have a quality of images which is equivalent to the previous one with a higher intensity. So this is really interesting. Dark noise suppression will hopefully obtain dose reduction. And what is remaining also, large dynamic range is also important because you have a counter. So you will be able for 1 pixel to count 2, and for the pixel just neighbor to count 1 billion. No problem with that. You don't have any problem for the dynamic range. So you can hope also to have better contrast. And at the end, the very important part is the presence of all these energy thresholds and the fact that you can select an energy. And this is the property that helps to develop spectral CT and color imaging and I will talk to it just a little bit after. Okay, 30 minutes remaining. It will be piece of cake. Okay. This technological breakthrough is coming from the LHC and particle physics. This kind of ASIC of hybrid pixel has been developed by CERN through the chip Medipix, several generations of Medipix, through the chip XPAD at CPPM. They have equipped the PixScan FLI, which is a microcity that we developed at CPPM, which is now at the Campus Santé La Timone. And it has been also used by Mars Bioimaging, which was a startup. Now it's a big company in New Zealand, who obtained the exclusivity for health application for the Medipix, and I will show you some images. Philips has developed also his own detector, Siemens also. So Philips and Siemens have now some spectral CT, well, let's say some CT with photon counting detectors. Installed Siemens in the US in 2 or 3 clinics in the US. Philips has been on his clinical validation at University of Lyon through a European project. And General Electric decided not to go through hybrid pixel, but to develop also a new approach, saying, okay, we will stay on the silicon detectors that are really well proved. And instead of using a face-on geometry, I will put the detector on the side, a very huge depth of silicon, and I will put electronics at different levels. The idea is that when you have a spectrum, a polychromatic spectrum that is arriving here, the low energy will be absorbed in first, and then the medium energy, and then the high energy will be the one that goes deeper. And you will be selective in energy through the depth of penetration. It's another completely different approach. But you also have to remind that with these new detectors also we are able to make some spatial resolution that are really thin, between 60 and 250 microns for this generation of detectors for spatial resolution range. Okay, I am, I think, a little bit late, so I will try. I wanted to keep this slide just to give an overview of the time scale of this kind of research from theoretical fundamental research to application in real life. Actually, the project of hybrid pixel started at the very early 90s and for the LHC, and the first image of XPAD in vivo was 10 years later. And 10 years later again, you will have the first publication jointly, well, in the same time by Philips, proof of concept, and by the CPPM and by the CERN, saying, okay, in vivo imaging, we are able to make some CT, photon counting, and spectral with this kind of detectors, and it works. And it is at the 2010 that all the big companies really invest in that program and develop some CT with photon counting detectors. And 2020, 10 years later again, the clinical trials are over and the first machine are in the hospital. So it took at least 30 years. Let's say more roughly half-time fundamental, half-time industrial development. And at the end, these machines are in the hospital. So just a few words about our camera, which actually it's made of chips here. It's made of barrettes, and each barrette is made of chips. Each chip, it's a little bit less than 10,000 pixels. And just for mechanical constraint, you will have to tilt slightly the images, and you have a raw data which is coming, which is like that, with a fast readout and electronics that allowed us to do more than 200 frames per second. Another example with a different sensor, CDTE, really more efficient at high energies. Here it's an example for crystallography. Here it's CDT is complicated to manipulate. So here you have the raw data, and you see that there are some dead spaces that you have to correct after to obtain this quite of images. The fast acquisition and proof of concept have been made also. Here it's a mouse under anesthesia, which some iodine injected, and which will propagate under on the heart. You have the heart beating, and will very fast go into the kidneys. And the interesting thing is to look at it in slow motion. So it's a differential movie. We subtracted the first image to all the others to see the differences, of course, and to see the trajectory of the iodine. But here it's an image with how many? I don't remember exactly. More than 100 images per second. And you can say, okay, you have to know that mouse, even under anesthesia, the heart is beating 6 times per second. So it's very fast, actually. Roughly speaking also, because I'm not a biologist. But this is the first movie that we produced when you can see the lungs and the heart beating, and then after all the iodine going through the elimination system, kidneys, and etc. So nice proof of concept, slow motion video in X-ray. Okay, this is the PIC-scan FLI, so the micro CT spectral that we developed, which is now at Cerimed in Campus Latimone for daily routine for biologists and medicines. So typically, this is also the opportunity for me to precise the 3 main blocks of a CT. The micro CT just means it's for small animal, not bigger than a mouse. And in this case, the animal is rotating around itself instead of the coupled detector and source is rotating around the patient. But everything is relative, so it's okay. And you have the first block, which is the X-ray source block, here with the wheel filters, 12 emplacement for metallic filters in order to modulate the spectrum and to avoid that the patient, the mouse, will be radiated with too low energies that are not useless, for the contrast. You will have also the animal block equipped with gas anesthesia, and this block is motorized in 3 directions for the translation, and of course with a rotating motor and rotating mode for the acquisition. And at the end, the innovation, the detector block. Here you have the X-ray, the X-PAD camera. Here you have the gold standard of CCD camera for a fair comparison. And camera and reconstruction here can be performed typically about 80 microns per voxel. In a maximum zoom, we can go to 45 microns for the size of the voxel of the reconstructed volume. So typically, this is the PIC-scan FLI. I didn't talk at all about physics. I will do now, okay, to describe a little bit about the acquisition. So, as I previously said, actually the X-ray imaging relies on the Beer-Lambert law, which describes how the matter is absorbed by photoelectric effect, or, well, with absorbed, how the matter absorbs, the X-ray. Okay, so, okay, let's go. Now, very simple example. Take a monochromatic case, go to a synchrotron, you have an X-ray source that is using only one energy and sending one energy with a flux I0, and go through an object here, for instance, which will absorb the X-ray source. The way of absorbing is decreasing exponential coming from the Beer-Lambert law, and you will have to integrate all the matter that is on the path along the line of sight, and you integrate here a little bit of absorption, more absorption here, etc. And then you will have this equation. The real life is not the synchrotron. The real life is a polychromatic case, saying that actually the beam is polychromatic. It has a spectrum, actually. So it turns out that the matter does not absorb photons of 20 kiloelectron volt than photons of 100 kiloelectron volts, actually. So you have to take into account the way that matter is absorbed depending on the material and depending on the energy of the incoming photons. So now you have a full spectrum arriving on the object. This full spectrum will be modified and absorbed partially, still according to the integral, according to the line of sight, but taking into account also the energy. So at the end, at the output of the object, you still have a spectrum something depending on the energy, which is arriving on the pixel of the detector. What does the pixel? It's an open question. Okay. What does the pixel? Actually, the pixel will integrate all the photons that are coming. So you will just make the integral according to all the energies between 0 and infinity, let's say maximum energy emitted by the spectrum. Okay. In real life, you will have to add some potential metallic filters that you want to use to modulate your spectrum. So it has a spectral response here of the filter f of A. You will add it. And you also have a spectral detector. Cool. This detector first have an efficiency depending on the sensor, the width of the sensor. So it does not acquire 100% of the photon. Some photons can be missed. So you have a detection efficiency that you have also to know and to introduce. And of course, an important thing hidden into this detector efficiency is the choice of the energy threshold. You will choose with photon counting detectors to count photons only the ones that are carrying an energy, let's say, above 20 keV or 40 keV. So actually, you will just put a lower bound on the integral. It is hidden in the detector efficiency curve, okay? And then you will be able to select in energy everything. Okay. So we want to do spectral CT. What does that mean? Okay, that means acquire different nature of measurements, selecting an energy and counting photons between 20 and 40 keV, between 40 and 60 keV, blah, blah, blah. So we're able to acquire that. But for what? Okay. Let's focus on the quantity of interest, the unknown, that we want to recover, which is the linear attenuation coefficient of the matter. It depends on the material, L, the nature of the material that you have, and it depends on the energy that is coming into. If you are looking at the physics, it's cool, because actually the first thing that you can do is that in my voxel, if I have several materials, actually I will say that the linear attenuation of everything in the voxel will be just the sum of the linear attenuation of each material present in the voxel, or linear combination of that. So first good news, if you have k components in your voxel, you can decompose your linear attenuation of the voxel into k different components. Second good news, for each elementary component taken in the Mendeleev table, actually you can decorrelate the energy variable and the material nature, actually. Actually, you will interpret this red coefficient as the concentration of the material times cross-section, which is the model of absorption of this material depending on the energy. Here you have some instance of sigma k of A for 4 different materials. Let's look at the water, the blue one, because it's a typical shape of how material behaves in the nature. It's a decreasing part. Okay, the higher the energy, the less the absorption. It's a log scale here. Okay, and three other materials: iodine, silver, and yttrium, which has the same global shape, decreasing, but have very specific discontinuity at specific energies. Okay, that we call the cage imaging, and that specific energy there is discontinuity, and the absorption is greater after. So I will come back to it later, but you know for each element in the Mendeleev table, you know the cross-section curve, and the idea is that the purpose of spectral CT is to recover each AK map, each 3D volume of AK, to be able to say, okay, in the volume of water, here I have some water here, I have some water here. In the volume of iodine, I have some iodine just in the heart. I have some iodine in the kidneys with this concentration, lower than, etc., etc. So the idea of spectral CT is to provide to the doctor not anymore one 3D volume of the anatomy, but k 3D volume, one 3D volume for each component, and in each volume, the interpretation of the quantity in the voxel will be directly a concentration, and not anymore a mean linear attenuation in Hounsfield unit or blah blah. So this helps to bring CT from a pure anatomic imaging to a kind of functional imaging, because you will be able to measure some concentration of different elements. Okay? Okay. I will continue. So if we want more output, K concentration maps or volume, we will need more measurements. And it's come back to the question, more measurements, more dose, and blah blah. Okay, I need K, concentration map, I need K measurements. How can I do K different measurements that will bring some additional information? Well, I need to have more information according to the dimension of energy, because how can I discriminate these curves? Because of their different signatures, so I have to be discriminant in energies. I will lose my thresholds, of course, and I will lose also some different setup in the polychromatic spectrum, different voltage, for instance, or I can change the metallic filters. So I will do several measurements, M measurements, that are different in energy. And I can play with my spectral response of the system, including the threshold of the detector, which is the most interesting part, okay, to produce some discriminating acquisition, discriminating according to the energy part. So I'm not doing one revolution with one CT scan. I'm doing K revolution with K CT scan. Each CT scan is different in energy because of the setup of the system, okay? And what can we expect about that? Why are we doing everything? Okay, let's once again take a toy example. This object, cylinder water, with some inserts with water, and also inserts with contrast agents, so things of interest for biomedical application, yttrium, silver, and iodine. And here is the standard CT reconstruction, given the fact that in my simulation, I cheated a little bit. The iodine, which is a very contrasted thing, is really in solution, very low concentration that can occur when you inject it in the human body, when it can fix on several cells, for instance. Standard CT reconstruction will help to see contrast, but first we don't be able to identify or to separate, to see that there are different contrast agents. And second, even for the low concentration iodine, it will be comparable to water. If you are able to do what you want with spectral CT and to use your discriminating information in energy, you will be able to produce 4 different volumes first, in which you will be able to identify which material where it is, to localize and to quantify, because here the level of intensity in this volume is directly a concentration map. So for instance, for the iodine, I didn't put the scale, but for the iodine, actually, it is here, and the concentration will be very low. In yttrium, I have different concentration in my yttrium, silver, and water, of course, the concentration will be of 1 gram per millimeter, is the density. So this is the ultimate goal of spectral CT. Today, this ultimate goal is reached, I don't know exactly, half reached. It's still an open question, actually. Okay. So the question is how to deal with this spectral CT now. There are several strategies. I will present 3 main categories of strategies. So the idea is that you will do M measurements, so you will have M different sinograms with each one having different spectral properties. You can reconstruct separately with your favorite reconstruction algorithm each sinogram and obtain M different reconstruction. And so with different concentration and different spectral properties. And at the end, take that and trying to separate, to extract the K components that you want. So basically, you can say that if you are familiar with some learning problems or IA or image processing, you can see it is a classification problem actually. It is already segmented by the reconstruction. In each localization, you can see the object, the part of the object. You want to classify it and to quantify. A very easy thing to do is to do some cage imaging. Okay, I will just focus now on what is the cage and to explain this discontinuity in the signature of the cross-section of here Iomeron, which is the biological product for iodine injected to the patients. Okay, so you have the decreasing the energy, the cross section here, or the attenuation. And at the energy of 33.2 kilo electron volt, you have the KH discontinuity for the iodine. And there is only the iodine in the universe that have discontinuity at this specific energy. So the localization of this KH here is specific of the object of the material. And what does happen actually? It means that if a photon is coming and making a photoelectric effect on an iodine atom at this energy, it will be able to eject an electron of the K layer, the more inside layer, and then there will be a reconfiguration of the atom, and actually the probability of doing an interaction at this energy will be lower than doing an interaction at the highest energy. So this discontinuity only comes from the fact that it allows or not to eject an electron of the K shell. Okay, and of course you will have lower some ML shell if you remind of your atomic courses of the structure of the atom and the electronic cloud. Okay, so it comes from that. But the important point is that the iodine has its energy at 33 keV, and there is only the iodine at this energy. So you take your detector, you can set up your energy threshold as you want. You will put one acquisition exactly at the KH energy, another acquisition a little bit below, another one a little bit above, and you will count only the photons in the band below the KH and above the KH. And the very simple exercise is to reconstruct both quantities with your favorite monochromatic algorithm, obtain two different reconstructions, and just making the subtraction. What happens? In the reconstruction for the band I+, in each pixel, for instance, in each pixel here, you will have a quantity which is actually the mean value of the attenuation. Okay, so we integrate in over a small band of energy, so the mean value here of iodine is over there. And on the other image, for the band I-, you will have, for the same pixel, a value which is the mean value of attenuation if the pixel contains iodine here. If you are doing the subtraction, you will have this quantity minus this one, so it's a positive answer, because this one is higher than this one. It's a positive answer for this pixel. And there is only the iodine in the Mendeleev table that produces positive subtraction between these two energies, because all the other material, including water in blue, will produce this one minus this one will be a negative answer. So actually a very simple way to identify iodine is to select in energy the band on which you will acquire your acquisition, your scan, and to reconstruct separately and make the subtraction. If a pixel is positive, there is iodine inside. If a pixel is negative, it's something else. I don't know what, something else. So in that way, you will be able, just by subtraction, to identify where is iodine, and the intensity is directly proportional to the concentration. Yes?
This approach only works with the injection of contrast agents. It doesn't work with different, for example, calcium deposits or iron deposits in certain parts of the body.
Okay, it's a very good question. It's directly linked to application, if I understand well. Okay. At the beginning of history of spectral CT, there was a lot of excitation because the idea was that we will be able to identify each organ. Stomach and blah, blah. In the abdomen, there is no contrast in CT. We'll be able to identify each organ, etc. Excitation has fallen down because actually it depends on the chemical composition, because everything is depending at the end of the nature of these curves, which are physically known. Okay, and it happens that forget these discontinuities. If you are taking the Mendeleev table up to atomic number equal to 20, 22, 24, it happens that this KH is existing, but it's very low and it's not in the window that the X-ray source can highlight. Okay, so you won't be able to use the KH as a discrimination. So at the end, you only have some decreasing curve. Of course, the higher the atomic number, the higher the absorption. So in the Y scale, for instance, calcium is over there. whereas water is over there. You can just expect to separate these two components because they are absorbing differently. But it's very complicated and very sensitive. So at the end, discriminating the organs was not an option because the absorption are too similar. What is done? The only thing is what is done is to separate the skeleton because calcium is really high in atomic number, higher than all the other material that we have in big quantity. Okay. So that is the one point. The other point is that above this limit of Z equal 22, 25, you enter in the range of materials for which the KH is visible in the X-ray range. In this material, only take what is biologically compatible, take the contrast agents, and at that point, yes, you can identify contrast agents, but you have to functionalize it, to inject it, and make them to do what you want, to fix the organ you want, to fix the metabolism you want. Okay. Okay, so some example here that we have made, 3 rubber with filled with one with iodine solution, one with the silver nitrate, and one with the copper sulfate as a standard solution. Copper sulfate, no contrast agent inside. Iodine and silver, 2 contrast agents. And actually, you see we can separate the map of iodine and the map of silver. And you will see that the section of the separated components are smaller than the plastic tube because the external shape of the plastic is made of plastic and not of iodine. So it is not appearing in these two things. Another example in a living mouse injected with iodine going to kidneys through the ureter and here the bladder. You can see, so this is the first images that we had. This one is nice. Actually, it is a standard CT reconstruction, and this is the maximum intensity projection obtained with a cage iodine CT, where you are very precise on the ureter that are more or less hidden by the skeleton here. And you can see typically the diameter is about 100 microns. So it works very, very well. Okay, but the problem is that when you are doing some in vivo imaging, first problem, there are movements. 5 minutes. Wow. Okay. Pas trop. There are some movements. Okay, and you want to deal with that. So this is the first example that we have made. One scan, and after the second scan, and the mouse is okay. The mouse has moved very low, but has moved even despite the anesthesia. So at the end, you will have some highlight signal here and low signal here due to the movement. So the strategy was to say, okay, just one scan and several energy in one scan. So you will differently set up the energy threshold in your detector, and actually you will sacrifice the spatial resolution to the spectral resolution, but you only do one scan, and then all the images can be superimposed, and then you can do the subtraction. A lot of noise here, of course, but you can do that. And the second advantage of that is that you are doing just one scan, so you are not increasing the dose, actually. So that is the good news. Okay, I have really few minutes only, so I will choose to go at the end for the medical application. I will, skip the very technical part. But if you want to talk about algorithm and inverse problem, no problem for that. We can do it during the lunch or during the coffee if you want. Okay, today, what is the main use of photon counting detectors? It is well established that the photon counting detectors, without speaking about spectral, just speaking about the fact that you are just using your detector in a photon counting mode, it is well established that the contrast is better, the quality of the image is better. Okay, so there was a really very detailed report on Siemens system before their commercialization, and clearly they say that the noise reduction and the dose reduction was achieved and really interesting for that. Another example, I find it really nice. It's about the monoenergetic images that you can produce artificially with spectral CT application. It concerns the problematic of cartilage. Here you have a normal cartilage seen as synchrotron. Synchrotron is the best spatial resolution that you can have, and monoenergetic will be a really better image that you can have. Okay. Here it is the same normal cartilage with a high resolution CT, standard CT, that can be done. Clearly the resolution is really nice. And this is virtual monoenergetic images obtained with a spectral CT. The resolution is lower, because it's the beginning of the story. The resolution is lower, okay? The contrast is good. Now take a pathological cartilage, and the pathology here is the presence here of holes and black regions pointed by the arrows. If you are looking, so it is seen as synchrotron. If you are looking with a high resolution standard scanner, you won't see anything there. If you are looking with a spectral CT, thanks to the gain of contrast and the better signal-to-noise ratio, despite the lower resolution, you can see, well, you have to trust me because through the video projector is not so obvious, but you have to trust me. You can see the holes here that appears, and the structures are visible and remains visible. Okay. At the end, for what also? For spectral material decomposition. Here it's an example of in vivo for mouse in the context of our study on the liver cancer. So you have a standard CT reconstruction here. The liver is marked with barium nanoparticles, and the decomposition helps us to isolate the barium and can see the tumor in negative contrast, whereas the water-like will include all the bones here that were on the same order of magnitude than the barium. Another example has been made on the good disease diagnosis, which includes uric acid, and calcium also is important for diagnosis. So thanks to spectral CT, you can isolate and identify and quantify and put it in color for a nice image, the uric acid, which is the signature of this disease. And you are also able to suppress the calcium to see the signature of the disease. And at the end also, a lot of work is done with gold nanoparticles that are highly biological consistent. And here this is a study done in Lyon by Salim Si Mohamed to mark the plaque, unstable plaque in arterial diseases. So the gold nanoparticles here will mark some unstable plaque that are potentially able to make some heart attack. So in the context of prevention, it can be very useful. And I will end, I promise, with Mars Biomedical Imaging images. So Mars Biomedical Images actually is a spectral CT, for only osteoarticular problems, so for arms and legs, that's all. And here you have two examples of spectral images that are produced. Here, nanovascularization done through gold nanoparticles, and here you have material decomposition that they identify fat in yellow, soft tissues in orange, bone in gray, and a screw that has been done in blue, so you can identify and quantify everything. Okay, I've done, and I will just conclude. Okay, 3 minutes later, and 20 slides. I will conclude. At the end, the photon counting is definitely the technology for CT now, but its use in the spectral CT context provides a lot of promises, but it's still in the context of research. The technology is now quite mature. The number of clinical applications is growing. It's mainly today focused on cartilage, articular, and also cardiothoracic application. And they are still looking for the killer application, which justify the fact that we have to use a spectral CT and nothing else. Okay, at the beginning, your question was, can we use something to identify organs or something like that? At the beginning, a lot of excitation, we will identify organs. Then after the excitation falls down, we will only be able to identify the contrast agent and so what. and the emergence and the lot of work about nanotechnologies, the ability that we have now to build some very specific nanoparticles just to target some metabolism, etc., brought a gain of excitation in the community of spectral CT, because they are providing the nanotechnology field is providing some tools that will be able to identify on the images. If the tools is able to fix a metabolism or organ, then we will be able to see an organ and to identify an organ. And of course, I did not talk at all about AI, but of course, all deep learning and learning are coming massively into the algorithm and help to accelerate, to provide better images and so on. Okay, I'm done. Thank you for your attention.